So I'm going to now shift into the next family, and it's the aromatics family. So we've talked about alkanes, alkenes, and alkynes, and now we're going to shift into aromatics. And so let's first draw a structure of what an aromatic is, because it's very specific as to what aromatics are. So aromatics look like this. They are a six-membered ring, meaning they have six, in this case, 6 carbons in the ring. So at first glance, it starts to look like a cyclohexane, but it's not cyclohexane, even though it looks very similar to one. And I'll compare and contrast that in just a little bit. But then you'll also see that they have this dotted line connecting them as well. So it has a solid line and a dotted line in between each carbon, like that. And I'll get to that. And then each carbon has one hydrogen attached to it. So that is the structure of an aromatic. Anytime you see that looking, when you see this 6-membered ring with the solid line and the dashed line between each carbon, that's indicative of an aromatic. Now these can be attached to things, so sometimes these hydrogens aren't there, or maybe there's a chlorine on there instead of a hydrogen or a fluorine. But the general structure has for sure 6 carbons in a ring structure where you have one solid line and then you have one dashed line. The dashed line means it's not a full bond. It means it's basically a half a bond. And so this solid line we know is a single bond, a carbon-carbon single bond, a carbon-carbon double bond. So we have a carbon-carbon single bond, we have a carbon-carbon double bond, and this means it's like 1.5. So this is 1 bond, 2 bonds, 1.5 bonds, and of course we know 3 bonds, right? So that dotted line means it's a half a bond. So anytime you see that, that means it's not a full bond, it's a half a bond. So it's like 1 electron being shared between those 2 carbons as opposed to 2 electrons in a solid line. So in this area right here, maybe there's 3 electrons being shared, is maybe the way to look at it. At least I think that answers a lot of our questions when we do it that way. So that's what it looks like. That's the actual structure of an aromatic molecule, is having that. Notice each carbon does have 4 bonds to it, because let's take one of these carbons. We'll take this one down here. Notice it has 1.5 bonds there, 1.5 bonds there, 1.5 plus 1.5 is 3, and then it has one more bond right there, that's 4. So it still does satisfy the octet rule. They do have all 4 bonds on them. They're just arranged quite differently than we normally see them. Now, this is the way this is probably the correct representation of an aromatic, but this is kind of painful to draw. And so there's shorthand notations for aromatics. And let me show you those, because this is what you really see. You'll rarely see what I just drew here. That's not typically how you'll see an aromatic. But let me show you some ways in which you will see an aromatic. So some people show them, or some books or some internet sites will show the aromatic like this. Right? And it looks like, now let me draw it with the carbons in place. I'm not going to add the hydrogens, but let me just highlight the carbons just so we're clear on where they are in this structure, because I know we're just learning them and we haven't used them too much. Right, that's what the structure above these 2 structures would be sort of similar, except the bottom one doesn't show the hydrogens. Each of those carbons would have 1 hydrogen on them, just like our structure there in red to the left. But it looks like this is an alkene, right? It's a cycloalkene because I can see a carbon-carbon double bond. But again, when you see this structure right here, and notice every carbon in here at this lower structure has 3 bonds to it, and then don't forget there's also the hydrogens to make the 4th bond on each one, right? Just as the one to the left there. And so it does set up very similar to the aromatic, but it doesn't look like it. But this is the way aromatics are shown in shorthand, is this structure right here. Right, that's an aromatic. It's just this structure is supposed to be represented, is really showing that structure right there. So that's one popular way to show an aromatic. So there, let me redraw that one major way. So this is the way I think you would most likely see it. Another way it's shown is like this, where it shows that, and then instead of drawing all those dotted lines between each of those carbon-carbons, they just draw a dotted circle in the middle, like that. Or, forget dotting it, they'll just do that and also show it. So all three of those is representation of this red molecule aromatic here. This is the proper designation, but no one ever shows it this way. We all understand that these three represent an aromatic. I don't care which way you use in the course, as I've always said, but you got to kind of recognize these a little bit because other sources will use these, and you have to be able to recognize those as being aromatics. I typically use this one, what looks like an alkene structure, but it is not. So what does that mean to us? A couple things. One is this is not, so therefore this structure is not an alkene. It's not an alkane, right? Alkanes have single bonds, and we've already said that these carbon-carbon bonds are not single bonds. They are bonds and a half. So these are 1.5 bonds. So they're not alkanes because they're 1.5 bonds. These are carbon-carbon 1.5 bonds, not carbon-carbon single bonds. They're not alkenes because they're not carbon-carbon double bonds, even though sometimes they look like carbon-carbon double bonds, as we see in this picture. And they're definitely not an alkyne. These aren't even close to carbon-carbon triple bonds. Let me show you what's not an aromatic. That's not an aromatic. That is a cycloalkane. Right? There's no representation for a bond and a half in there anywhere. So these are all carbon-carbon single bonds. That's a cycloalkane. In fact, it's a hexane, is what the cyclohexane, because it's got 6 carbons in the ring. All carbon-carbon bonds are single. This is also not an aromatic. No, it doesn't match this structure in the upper left. It only has one representation of a carbon-carbon double bond. So that truly is a carbon-carbon double bond. And so this is a cycloalkene, because it has a carbon-carbon double bond. So that's a representation of a cycloalkene right there. And in fact, it is a cyclohexene is what that is, because it has 6. Now, you'll never see aromatics don't have 5 carbon ring structures like cyclopentenes or pentanes. It doesn't have that. It doesn't have cyclobutane. It doesn't have 4 carbons in the ring, never has 5, never has 7. It has to have 6. And it must have the structure as we see shown there. So it'll be very clear. So these down at the bottom, these 2 at the bottom, are not aromatics. Even though they sort of look like them, they are not. They must have this bond and a half structure. So I'll get to some naming of them in just a moment. And we'll kind of get in there when we get to reactions. We'll do the naming at the same time. But let me talk about properties of aromatics. Now notice they have all carbons and hydrogens or carbon-carbon bonds, or I should say carbon 1.5 bonds, but they're still carbon-carbon bonds, whether it's single, double, or triple. So these are just like the alkanes, alkenes, and alkynes. They're just carbons and hydrogens. So therefore, they're going to have properties very similar to that. One, just like the other ones, they're nonpolar. Right, because carbon-carbon bonds are nonpolar and carbon-hydrogen bonds are nonpolar. 2, because they don't solubilize with polar molecules because they are nonpolar, we already know they are insoluble in water. So they don't mix with water well. And 3, just like alkenes, alkenes, and alkynes, they are flammable. So you can burn them very easily. Now, one major difference between these is that this aromatic ring, which I don't know if it's really, or these aromatic rings are very non-reactive. They don't react very well. This bond, this ring structure, that bond, that carbon-carbon bond and a half, does not break very easily. So therefore, when you see this structure drawn, like the one we have over here in the upper left, when you see that structure, although you want to think it's a carbon-carbon double bond there, and we know we just learned alkenes and alkynes, those carbon-carbon double and carbon-carbon triple bonds just love to break, right? They just love to react. These don't. These bonds and a half don't. And the reason is, and I'll just say very briefly, and I don't want to get too deep into it, but the reason is because this structure right here, the reason people like this structure is because those bonds and those extra half bonds on each one are actually shared equally through all of them, and it very much stabilizes the structure. So by breaking one of those bonds and a half removes all the stability of that ring structure. That sharing of that half bond between all those carbons actually forms a very, very stable structure. And so it's very difficult to break the bond in half, because by breaking the bond in half, you're more than just breaking the bond in half, you're removing all the stability of that structure. So that extra half bond stabilizes it very, very well. And so it's not like you're trying to break a bond in half, it's you're trying to remove the stability of that structure, and that's just very difficult to do in normal reactions. You can break it, but it takes very, very harsh conditions to do so, so it's not really normally done. So since we're talking, like in the laboratory, you could break that bond in harsh reactions, but we're kind of gearing up to get into living systems, and so living systems really won't break that bond, that aromatic ring very easily. So when you look at reactions with aromatics, don't break those carbon-carbon bond and a halves. Don't do that. It's too stable. So let's talk about the reactions of aromatics. And before I get into those, I want to kind of make a couple of comments about reactions overall and things that we typically see in biochemistry and organic chemistry, and organic chemistry that relates to biochemistry. In our alkenes, when we studied alkenes, notice what we did. We took an alkene, right, and we added something like H2. And no matter which one we did, they're all the same. And what we got in the end was a molecule like this, right? We called this general type of reaction an addition reaction, because notice what we're doing. Much like an addition equation, where we take 4 plus 2 equals 6, notice we start with two things, we put them together to make one thing, right? It's an addition. These are called addition reactions, right? And we sometimes show this addition reaction by going A plus B, in this case A being the alkene, B being the hydrogen, and C being the product, right? So it's an addition reaction. Two things come together to make one thing. So we call that an addition reaction. Alkenes and alkynes are a series, all those reactions that we learned are all addition reactions. If you go back and look at them, it's like the alkene or the alkyne plus something else made one molecule. In reactions of aromatics, we're not going to see addition reactions. The kind of reactions we're going to see are substitution, where we actually take part of one molecule and break it off and add it to another molecule. In exchange, part of that molecule goes to the other one. Let me show you that in letter form. So let's say we have the molecule AB, so that's one molecule, and we have another molecule CD. In a substitution reaction, we're going to take part of AB, in this case we're going to take B, and we're going to move it over here, and we're going to take part of CD and move it over here. So in the end, what we end up getting is AC plus BD. Notice we didn't add them together. Notice we started with two things and we ended with two things. We took part of one molecule and part of another molecule and just switched them. So we call those substitution reactions. Notice substitution reactions are quite a bit different than addition reactions overall. So let's take a look at some substitution reactions that aromatics undergo. And then we're going to look at two of them. One is nitration reaction. Nitration is NO2. So let's take an aromatic, and I'm going to draw it in one of the simple ways. There's my aromatic. But I'm going to, now normally I would not have to put the hydrogens on this, but I'm going to put the hydrogens on it because they're going to be part of the reaction, so we want to see them. So this would not be the real perfect way to do it, but when I'm just showing a reaction, I think we need to see the hydrogens. So there's one molecule, and going back to our substitution designation, this would be AB. And to that, we're going to add this molecule. And this is nitric acid. And notice I've already broken it apart into the two pieces. There's a piece here, the OH, and here's the nitrate group right there. But that would all be together. You know, typically this would be written as HNO3. So if you go in your chemistry textbooks, this is probably what you'll see for nitric acid. I've broken off the O and the H and left NO2. So I've just kind of split that because that's how it's going to break. So in our general reaction for a substitution, this would be CD, where C would be like the D group, OH, or OH would be D, and NO2 would be C. And what we're going to do is we're going to switch them. We're going to switch pieces. We're going to take this NO2, and we're going to switch it with one of the hydrogens. So one of the hydrogens will come on over here. And what we'll end up with is our aromatic and it has an NO2 on it, plus, what are we left with? The OH that we started with, and then we added another H, so that's just a molecule of water. So notice this is, the products are AC, and the other product is BD. So we just switched them. So notice how we just switched pieces, but we ended up with two molecules to start with and two molecules to end. Notice I've mentioned before that aromatics are not reactive. What I meant by that is you'll never break the ring structure of the aromatic. So notice this reaction doesn't break the ring structure at all. It just flips out one of those hydrogens. In our second reaction, it's a halogenation reaction, so we know what a halogen is. So we can probably start to guess what a halogenation reaction is. And just as a reminder, halogens are things like Cl2, F2, I2, Br2. Right, that's the way they exist in nature. They're all diatomic. They're not single atoms, they're double atoms. And we can take our aromatic again, and again, I wouldn't normally have to show the hydrogens. I'm just going to show them because they're going to be part of the reaction, so we want to be able to see them. So I'm going to put them in here. And this is another substitution reaction. So in this case, we'll do Cl, Cl. So again, this is AB, and the B here is one of the hydrogens, plus CD. The C is chlorine and D is a chlorine. And all we're going to do is we're going to take the chlorine and switch it with one of the hydrogens. And what we get there is the aromatic. Again, notice we didn't break the ring because the ring is very, very strong. It's hard to break that ring structure. But now it has a chlorine on it as one of its atoms. All the other hydrogens, the other 5 hydrogens are there, but this would be the correct way to draw it now. You don't have to draw the hydrogens on there when you have a skeleton structure, as I've shown there. And then notice what we're left with. We have the remaining chloride, but now a hydrogen's bound to it, and we have an acid hydrogen chloride. So these are the 2 major reactions of aromatics. And again, notice that neither of them break that ring structure. They all just kind of chop off one of the hydrogens and replace it with either a nitrogen or a halogen. Now, before I get into naming aromatics, I want to kind of just walk back through substituents, and substituents that we've seen, ones that we're just starting to see, and then ones that are to come. So this will be kind of our full list for the semester. They won't get any more than these. So the first group of substituents that we've learned is the alkyl groups. Now, alk is kind of short for alkane in this sense, but remember, as when they're named as a substituent, they have that YL designation. But we call them alkyl groups because they're like little alkanes hanging on there. And these are things like methyl, ethyl, propyl, isopropyl, things like that. Things on that chart that you'll get on the exam and quizzes when you need them. So we've learned those already. We feel comfortable with those. We have the halogens. And this is things like bromo, chloro, fluoro, iodo, right? So you have those guys. So we've learned them as well. We just added a nitrogen group onto an aromatic, and that is the way you would write that in a name would be nitro. So when you see nitro in a name, it is, and I'll put the little line there, the connection point, but it's an NO2 hanging on to the group. And again, that line in front of the NO is how it attaches onto like that carbon chain. So when you see an NO2 hanging off a carbon chain, you would use the substituent. That substituent would be called nitro, like methyl or bromo. You have nitro. One we haven't seen yet, but that will be coming, is amino, and that's when you see something that has the designation NH2. So when you think about amino acids, you may have heard of those before. That's an amino group right there. That's part of amino acids. So we'll be using that. We'll be talking about that guy a lot. One I briefly mentioned at one point is hydroxy or hydroxy group or hydroxyl. And that is an OH group hanging on to a carbon chain. And then the last one that we'll need for the naming today, or at least the naming of these guys, these aromatics, is phenyl. That is when you're naming a aromatic as a substituent. And instead of one of those H's, you connect onto the carbon chain. And if you see something big old aromatic hanging onto a carbon chain, you'd use the word phenyl. So that would be the group. Notice it ends in YL, just like methyl does, but it says phenyl. And it doesn't make sense why it's not arol, like something like that for aromatic, but it's not, it's phenyl. So phenyl is basically just an aromatic ring hanging onto a carbon chain. So this is your group right here. This would be a nice to kind of put to the side as sort of a summary of all the substituents that you'll have learned in the course. So let's go ahead and name or work on naming a little bit here for the remainder of this video. So let's name aromatics. So again, once you identify Aromatics are kind of strange the way they use their terminology. So there's a guy. We know that, so we look at that. So how do we name this guy? It's the family. We first, again, as we name anything, we first identify the family. And the family is the aromatic family. But how do we name it? Kind of like when we name when we figure out alkane family, we say, oh, in the naming we use ANE. Or alkene family, oh, it's ENE in the name. Alkyne family, oh, it's YNE. Aromatic family, what's it? Weirdly, it's benzene. I don't know why. There's historical reasons as to why it is, but that's the name. So when you see benzene in the name, it's an aromatic ring like we see here on the left. So when you've identified as a family member of an aromatic, you name it as a benzene. Because there's now no substituents or anything on it, that's what that is. So there's benzene. Let's go ahead and change this structure now, and we'll start again. So again, identifying the family starts us all off in the naming. So here's a structure. We're going to do this one. I'll put a chlorine on there. So that's a Cl. Sorry, that's terrible looking Cl. Let's see if I can draw it better. There we go. Okay, so again, we look at this structure and we say, oh, it's what family is it? It's the aromatic family. It's not the benzene family, even though I know that would make much more sense. It's not. The family is aromatics. And so once I've identified this as an aromatic, I go ahead and put benzene on the name as a suffix. Now I go ahead and start naming my substituents. And I see a chlorine on there, and so that's chlorobenzene. You could put one chlorobenzene on there, but because there's only one on there, there's only one spot to put it. And again, that's one chlorobenzene. If I were to move this over to here, that's one chlorobenzene. Remember, you can turn this benzene ring like a tire. And so if you turned it like a tire, you'd eventually turn it to the point where the chlorine is right there. And notice it looks just like the first one. So if you just have chlorobenzene, all the positions are identical. They all are the same thing. So that would be chlorobenzene right there. What about this guy right here? Go ahead and pause the video and come back and see if you can name this one. So again, I look at this structure and I see that there's a benzene ring, and so or an aromatic ring. So this is the aromatic family. Once I identify as an aromatic family, I go ahead and put benzene, and now I name my substituents. And so I can number the carbons of the ring, and again, I got to get my substituents on the lowest number possible. If I start at the chlorine and work my way this way, I will have something on the 1, the 2, and the 4 carbon. If I start at bromine, so let's go ahead and get rid of this. Here I can start at nitrogen, and I can go this way. That would be 1, 3, 4. So that's not right. 1, 3, 4 is bigger than 1, 2, 4. So that's not it. So we can get rid of that idea. And we'll try one more way. Wonder if I start with bromine, chlorine, and went this way, it would be 1, 2, 3, 4, 5. So 1, 2, 5 is still bigger than 1, 2, 4. So I think I got my numbering down. It's going to be 1, 2. It's going to be chlorine. This will be the 1 carbon right here where chlorine is. 2, 3, and 4, and eventually 5 and 6, but I don't need those. And so then I'll put these in alphabetical. I don't think I have enough space to write all this. So I'm going to write above it. It's going to be 2 bromo, 1 chloro, because this is alphabetical, and then 4, remember this is our new one, nitro benzene. And this is an interesting one to name right here. Go ahead and give this one a try, see what you come up with, and then come on back and we'll name it. Okay, so since we're working on aromatics, I can try to name this as an aromatic family. And so I see my benzene ring, so I'm going to name it as aromatic, so it's benzene. And then I see something hanging on it, and if you go look at the substituent chart from the textbook that you'll get on any exam, you'll see that when you got 4 carbons in a row like this, and the end carbon is the one that's attaching on to the family, or in this case the ring structure, that's the 4 carbons in a row is but, so this will be butyl, because I'm using it as substituent, kind of like methyl, ethyl, propyl, butyl, right? As you go on, we just keep pentyl, be 5 in a row. We can do that. Now, if it was attached to a different carbon, in this, like the second carbon, it wouldn't be butyl, it would be something different. And again, it's on that chart. So that's butylbenzene. But some of you may have said, well, I'm going to name it as an alkane, and you can, right? I can name the carbon chain as my alkane chain and name the aromatic ring as a substituent. So let's name it as an alkane. So it ends in ane, because it's an alkane, because I'm naming, just to be clear, I'm naming this, and I'm naming the phenyl group there as a substituent, so I don't need it in my family. So there's it's an ane. It's got 4 carbons in it, so it's but. Whoops, my color changed on me. So it's a but. So it's a butane, right? And now I have a substituent on it. I want to get the substituent lowest number possible, so that'll be on carbon 1, because here's carbon 1, 2, 3, and 4. And what is that hanging on there? Now, when it's named a substituent, you would want to think that it would be benzyl, right? Just benzene, but with the YL, but it's not. We just learned when we talked about substituents, it's phenyl. Again, I don't understand, they're just making it confusing for us. So the family is aromatic. When you name it as a family in the name, it's benzene. But if your name is substituent, it's phenyl. So there's a phenyl ring. And where is that phenyl ring? It's on the first carbon, so it's 1-phenylbutane. Either of those 2 answers are acceptable. And so either one will work. So sometimes you can name it as a family, name it as multiple families. And so for this one, I don't care which way you do it. Okay, go ahead and for the last one, go ahead and try to name this one, then come on back and we'll chat about it. Okay, so we see this structure here, and we say, okay, it's part of I see an aromatic ring, so I'm going to name it as an aromatic. So we'll go ahead and put on benzene. And then we need to name the substituent, and we need to name this guy. And so we go to our chart that we're given, because we don't know what that is. That's not pentyl. Pentyl would be if it was attached to the end carbon, not the middle carbons. So if we were attached directly, if the attachment point was on the end carbon, let's say like to this carbon, then it would be pentyl. But it's not. So it's not pentyl, it's something else. So we go to our chart, but on the chart you'll see that this structure is not shown. There's nothing on that substituent chart shows 5 carbons on it. It only goes up to 4 carbons. This does have a name. This does have a substituent name, although it's not on our chart, so you don't know what it is. You could go deep and look in the internet and find it. So unless you did that, you wouldn't really know what this is. And so therefore, because we don't know what this is, maybe this is not a good way to name it. There is a way to name it, but it's beyond our need, and you won't need to know how to name this. But what you need to do if you see something like this and you're like, I don't know what that is, well, try a different approach. Let's go ahead and try to name this. Let's go ahead and not try it as a benzene. Let's try it the other way around. Let's put benzene as a substituent. What do we have left? Well, now we can name it as an alkane. So I see the ane, and so we just need to name it. What's the longest continuous carbon chain? I see 5. Now remember, when you do longest continuous carbon chain, you don't go, let's say 1, 2, 3, and then go into this ring structure. You can't do that. Just like with cyclos, you don't go outside the ring, you just name the cyclo ring. So you never do that, so we can't do it that way. You have to go on the straight chain. Either you stay on the straight chain or you stay in the ring. You never mix the 2 when counting the longest carbon chain. So we have that. So we can just go 1, 2, 3, 4, and 5. And so this is pent. And then we just name our substituent, which is right here. And that's a phenyl group. And notice no matter which way we number it, the way we did, or if we try numbering the other direction, 1, 2, 3, 4, 5, it would still be on the 3 carbon, and so this would be 3-phenylpentane would be the best way to name that.